Hi, we're going to look at finding limits of equations in this video, and we're going to focus on one-sided limits. So you can see on this one, we're letting x approach 2 from the left. That's what that minus sign means right there. Okay, so one thing that you might notice is that this is a pretty simple equation. This is just a function. This function is just a parabola, and so it's pretty easy. There's anything weird going on with that. And you might say, well, if this were just a regular double-sided limit, just a regular limit, the limit as x approaches 2 of x squared plus 4. We would know how to do that. We have a substitution shortcut theorem that talks about for polynomial functions, you can just substitute. And so we're actually going to be able to use that, but there's a theorem that we need to make sure that we're thinking about as well. So when we first introduce one-sided limits, one of the important things is a theorem that talks about relating regular limits. The limit as x approaches a of a function. And if that limit is L, that is an if and only if statement. So that's a double implication. So that means if this is true, then the following part is true as well, and the other way. So if this limit is some number L, then both of the one-sided limits, both of them, are the same value L. Let me put an and here, so that's important. The limit as x approaches a from the left of f of x is also L. So both of those limits will also be the same. And so this is an if and only if theorem, which is a really powerful theorem. So if I know this limit is something, then that tells me about these. Or if I know about these, then that tells me about the original limit. Okay, so we have some theorems for this kind of limit. Substitution shortcut theorem for polynomial functions. So there's nothing weird going on in this function around x equals 2. So when x is close to 2, it's really doing the same thing that it's doing when x is actually at 2. So we can use a substitution shortcut theorem and just substitute that 2 in there, simplify this, and we get 8. Right? So that's a substitution shortcut theorem. And then we can use this theorem that's about one-sided limits and regular limits. And we can then conclude that that limit of this original problem here is also 8 by using that theorem. The one-sided limit theorem is usually what I call that, if you want to justify what theorem it is you use. Okay, so we're going to look at another limit problem here, a little bit more difficult. We're going to this time let x approach 1 from the right, and we're going to look at a square root function, square root of 2x minus 2. So at first glance, you might think about just trying to use this same theorem that we used for this last problem on this one. You do have to be a little bit careful about that, though, because this function, unlike the previous function, has some domain restrictions. So the polynomial function that we started with has no domain restrictions. It has no problems with that domain anywhere. But this function actually does have some domain restrictions. And so you want to think about those first and make sure that you're clear about what's going on with that. All right, so when you think about a square root function, the domain restriction is that that expression inside the radical has to be greater than or equal to 0 so that you get real valued outputs. So if I write that inequality, 2x minus 2 greater than or equal to 0, and then solve for x, I get x greater than or equal to 1. All right, so this one-sided limit is asking us about what is happening to this function when x is a little bit bigger than 1. And so that's OK, because that is actually in the domain of this function. If it had been asking us about as x approaches 1 from the left, when we're less than 1, then we're going to have to think a little bit more about that. OK, so for this one, though, since we're approaching 1 from the right, which is in the right side of the domain here. The domain is at x equals 1 and then greater than that. We can go ahead and do this. I'm going to do a little algebra simplification just to make this a little easier to think about. I'm going to notice that I can factor out a 2 inside that radical. And then when I think about this, when x is close to 1, but a little bit larger than 1, we're going to be close to, this expression inside here is going to be close to 0. So at this point, I'm not really using this theorem about two-sided limits here because the domain of the function does not include the left side of 1. All right, so for this one, I really could just have to think about the one-sided limit. I just have to think about when x is greater than 1. So this part here is going to be close to 0. So that's going to be close to the square root of 2 times 0. And so 2 times 0 is 0. Square root of 0 is 0. So that limit is 0. Notice I mentioned this, but I'm going to go ahead and write it down as well, that if we were looking at the limit as x approaches 1 from the left of this same function, that's a little bit more tricky. And the temptation is to kind of do the same thing that I did on some of these others and substitute x equals 1 into that one, but you can't do that. Remember that this function has a domain restriction. X cannot be less than 1. So x cannot actually approach 1 from the left on this function. So for this one, we would say that this limit does not exist because x less than 1 is not in the domain. We cannot approach x equals 1 from the left. Okay, so going back to this two-sided limit theorem that we have over here, where we have this double implication talking about if we know something about the limits from either side, what that tells us about the overall limit and vice versa. In this first example, we use that theorem this way, where we decided that the limit, the overall limit, was 8, and we used that to infer that the one-sided limit was also 8. For this one, we're going to use the theorem the other way, right? So what this says, we've got a limit being 0 here, but this other limit does not exist. So because those are not both true, then I cannot conclude that that overall limit is 0. All right, so the one-sided limit here is 0. The one-sided limit from the other side does not exist. And so we would also say for this one, because those don't agree, that the limit as x approaches 1 overall for this function would also not exist, does not exist. Because of this theorem here, those two one-sided limits have to agree in order for the overall limit to exist. Okay, so we'll look at some more examples of one-sided limits from equations and graphs and using some more theorems about that.